Hello everyone, I'm Daniel Misha from the Institut Photovoltaic d'Île-de-France, IPVF, and I'm here to talk about my work on the optimization of diffraction gratings for multi-resonant light trapping in ultra-thin solar cells. This is the outline of my talk. I will start with a brief introduction talking about light trapping. Then I will proceed to the state of the art of the technology, talk about the methodology and the results of our work, and finally the conclusions. Ultra-thin solar cells are devices in which the thickness of the absorber is much smaller than the absorption length of that material. To being that thin, it brings several advantages, such as low cost, flexibility, lightweightness. The cells can be very highly efficient and radiation hard. But to go that thin, light trapping is required to avoid transmission losses. So here in the right of the slide, we see three different approaches for light trapping. The first one is the simplest one, with a backside reflector used after the structure, which will allow for double pass of the light inside the structure. The second mechanism here, the second approach, is Lambertian scattering, in which one of the surfaces is textured, allowing for random scattering, lateral scattering of light inside the materials, and subsequent confinement by total internal reflection. The third approach is also based on lateral scattering, but by a periodic patterning of a layer that can be in the front side, in the back side, or in both. So here is, I show you two different plots for the same figure of merit, which is the short circuit current, which is the mostly impacted figure of merit when you go ultra thin, as a function of the thickness for silicon in the left side and gallium arsenide in the right side. So we see in this plot three different lines. From the bottom to top, we see the limits for single pass absorption, double pass absorption, and Lambertian scattering. And as we can see, there are few results overcoming the double pass absorption. Here for silicon, we see these dots represent actually theoretical results from the literature, the open dots, and the closed dots are for experimental demonstrations in the literature. So we see below 10 micrometers, we see only 1, 2, 3 results for silicon, and for gallium arsenide, we see only 1. So I'm going to talk a little bit more about these 4 results. So we see here in this slide the 3 of them. Okay, so the 3 results here are for silicon, the 4 of them, 3 for silicon and 1 for gallium arsenide. And what all of them have in common, which is interesting, is that they use a subwavelength periodic patterning as an approach for light trapping. So this seems to be a very reliable, efficient way of trap light inside a solar cell or any structure, and this is what we are going to use in our work as well. So furthermore, in all these studies, it's nice because they also do a very detailed analysis of losses in the devices, showing where it could be improved, and also discussing about the physical mechanisms behind the absorption enhancements they have in the structures. So, having learned with the literature, with the studies in literature, we are now proceeding to our work. Our problem here is to optimize the optical structure for a 100 nanometer gallium arsenide ultra-thin solar cell. And I'm showing you here 2 different ways that we use to do that. First, I will say that all the optical properties of our study were obtained by RCWA method, which is a method to solve the Maxwell's equation in multi-layered structure, especially when you have patterned layers such as diffraction, the use of diffraction gratings. But we didn't implement RCWA ourselves. We rather used Reticolo, which is a software developed by people in the Institut d'Optique in France. So we follow two approaches in this optimization. One is a genetic algorithm in which the objective function is the equivalent optically short-circuit current, which is calculated with this formula using the absorption in the active layer in the solar spectrum, AM1.5G. And when we have this equation, we are considering actually a carrier collection efficiency of 100%. A second approach was with physical description of the mode, trying to understand the physical mechanism behind the enhancement of absorption in our structure in order to go further in the optimization. Okay, here I'm showing you the step-by-step optimization process that we've done with our structure. So starting here in the left with single and double pass absorption in a gallium arsenide, 100 nanometer of gallium arsenide slab, we can see here in the graphs of spectral absorption that the GaAs, the equivalent GaAs of this single pass is just 11.5 milliamps per square centimeter. In the here in solid line, we represent the absorption in the active layer, and for double pass, it goes up to almost 16 milliamps per square centimeter. When we implement, we start implementing the optimized optical structure. We start by using a semiconductor dielectric diffraction grating, and also introducing a spatial layer between the metal and the grating, which has been shown previously in other works, to minimize or to reduce a parasitic absorption, especially in the metal by plasmonic resonances. And we can see that we gain almost 10 milliamps per square centimeter in the optically equivalent GaAs. Okay. Finally, we ran our genetic algorithm approach, optimizing and changing all the several parameters here, almost all the thicknesses, except obviously the gallium arsenide, because we want to stick to 100 nanometers. We changed also the refractive index of the materials, trying to find the best materials for our structure. We also changed the grating dimension. So the search space in the end for our structure, our genetic algorithm, is more than 10 variables, which would be very difficult to do by hand. And after several runs of the genetic algorithm, then we finally found our final result, which is 27 milliamps per square centimeter, a very high current. And when we look into the plot that I showed you previously, we see that this is the highest current for this thickness range, which is a very, very good result, impressive result. Okay, here in the right, I show you a detailed analysis of losses in our structure, and we can see here as colorful solid lines the parasitic absorption in the different layers. In black, for the active, which is not parasitic, is the proper absorption for the GaAs. But we can see here that the cladding layer, especially window and back surface field, contribute to the highest parasitic absorption of around 1.5 milliamps per square centimeter. And actually, in the end, we can expect that part of this current will be collected as GaAs, and this current can be even higher during the experimental demonstration. The main source of loss in our structure is reflection, actually, with 3 milliamps per square centimeter. And it happens, it takes place especially here in this wavelength range of 750 and 850 nanometers. This red dashed line is the reflection in our structure. Trying to understand further the physical mechanisms behind our absorption enhancement peaks, we proceeded with a study on the physical mechanisms, and hopefully we could use this information, this understanding of the physical mechanism, to maybe tune some of the absorption peaks in this region, trying to optimize even further our result. So here I'm showing you in the left the calculation of the propagation constants for our structure. So propagation constants are nothing more than the eigenvalues of the wave equation for a multi-layer structure. So we have here the wave equation, which becomes an eigenvalue and eigenfunction equation by using the properties of the propagation in a multi-layer structure with a plane waves. And we can see as eigenvalues here, we find the vertical component of the wave vector, which can be written as a function of the in-plane wave vector, which is a constant through the structure. So that's called the propagation constants. And here is the calculation for the different polarizations, TE and TM, in our structure, and we can see the different propagation constants. Okay, on the other hand, we have the diffraction grating. And the diffraction grating introduces the lateral scattered modes. So here is the equation for a square grating under normal incidence, showing after the incidence of the normal incident light, all the orders which are laterally scattered, named here by this code, this 1, which is the order of this diffraction order. And the in-plane wave vector of this order can be written with this formula, in which P is the period of the grating, Mx and My are integer numbers, labeling these different orders. We are here using a different naming system, nomenclature system for our orders. We are now rather calling them optical states, in which an optical state is the sum of the squares of the indices. So we can see that OS1 can be either Mx equal plus minus 1 and My equals 0, or 0 and My plus minus 1. Okay, here then we have what? We have in left the modes that can be sustained in our structure, and in the right we see the modes that can exist in our structure due to the lateral scattering of the grating. Now we need to combine these two information to understand which modes are being excited by our grating, and we did that by plotting this new graph with the superimposed horizontal lines representing the diffraction grating modes, the optical states. So whenever there is a matching between the diffraction grating modes and the propagation constants, we will have an excited guided mode. So it means that that mode is excited by a grating and can be sustained in this structure. By finding the matchings between the different curves, we can superimpose these vertical lines in our absorption curves, showing where we have the excited guided modes, and trying also to get an understanding of which mode is contributing more or less to a given absorption peak. So we see that several modes actually well explain the absorption enhancement especially in the short wavelength range. In the long wavelength range, we have some open questions here, but even though we have good matchings with the peaks and the excited guided modes. All right. Up to this point, we have described the excited guided modes and how they can explain the absorption peaks, but one information is missing here. We don't know yet how much energy is being directed to each excited guided mode. So we now are going to add a new contribution to this framework, which is the calculation and actually the use of the information of the diffraction efficiencies. Diffraction efficiency is actually the amount of energy which is directed to a given diffraction mode, and in comparison to the incident power. So it's the power in that mode divided by the incident power. So here in the right we have a plot of the diffraction efficiencies as a function of wavelength for the different optical states in our structure. So we can see that they have a wavelength dependency, and this information is important actually to understand not only which excited guided mode exists in our structure, but also the strengths of the coupling between the grating modes and the propagation constants in our structure. So in the left, what we did was to update that plot with this new information, which is the diffraction efficiencies of the different optical states. So the horizontal lines here represent the optical states, and in colors now we represent the efficiency of that optical state as a function of wavelength. So we see that as more reddish, we have a higher diffraction efficiency, and more to the blue, we have lower, or to the black actually, we have lower diffraction efficiencies. So some matchings here, for example, G's excited guided mode in principle should not be contributing too much to an absorption enhancement, because the amount of energy being directed to that excited guided mode is very low. On the other hand, when we look to these two matchings here, these two excited guided modes, we see that they should be contributing very strongly to the coupling of the modes in the grating and the modes sustained in our structures. So this is a new addition to the literature, the contribution of the diffraction efficiencies to this understanding. Going further, we can also use this information to optimize, to keep optimizing the structure, as I said before. So here I show different plots. This is a very interesting way of plotting the diffraction efficiencies as a function of wavelengths. Here we are plotting all the diffraction efficiencies. In the previous slide I only showed the strongest ones, but here we are plotting all the diffraction efficiencies of the structure, so they should sum up to 1 when there is no absorption. And in this case, yeah, to obtain the diffraction efficiencies in our structure, we actually had to do some changes in the structure, but I'm not going through this here because of the lack of time. But what's interesting here is to see that different patternings of the gratings. So here I'm showing for square gratings. Actually, the gratings is square, but the patterning inside is square. For square gratings with circles and square gratings with triangles, this is a tentative of doing a triangle numerically, how the diffraction efficiencies measured here by different colors for different diffraction orders change. And we can see that we can actually use, we can engineer the structure in different ways in order to have higher or lower diffraction efficiency in given orders, to try to increase the coupling between a given diffraction order, a diffraction mode, and a propagation constant. So this can be very useful for further optimization of the structure. And we can also see, we can study the influence of asymmetry. So for example, here we see very symmetric contributions for all the diffraction orders for symmetric patternings. And when we have an asymmetric patterning, we start seeing different contributions for the different orders not symmetric. So to conclude here, we showed in this work a very optimized optical structure for a 100 nanometer gallium arsenide ultrathin solar cell with an optically equivalent GaAs of 27 milliamps per square centimeter, which is one of the highest value ever achieved for this thickness range. We can see here in this table that our result is high. Actually, looking only to the current is not the best figure of merit, but also instead we should look to the ratio between the achieved current and the maximum current that can be sustained by just by single pass absorption. And we achieve a very nice result of we have more than two times the amount of current that can be passed in single pass absorption. We also extended the frameworks shown previously to describe the strengths of the excited guided modes in the structure using a new figure of merit, the diffraction efficiencies. And as next step, we intend to use this new information, this new physical description, in order to tune some absorption peaks in the wavelength range of 750, 850 in our case, because it's the range in which the reflection is high, to reduce to minimize this loss even further and increase our result. And with this, I would like to thank you for your attention. This is my email, and if you have any questions, please don't hesitate and get in touch with me. I'll be very happy to answer your questions and any proposal of collaboration. Thank you very much.